Okay, so last week we proved the second symmetry for the tetrahedron. So let me summarize now about these two symmetry. The order in which the morphism appear in the right-hand side of the first equality. So you have the previous proposition. So this one we proved here. The first equality is here you have only one equality. So the order in which the morphism appear in this equality compared to the order which is here. So you have this first equality and this one. The order, you have that, and the order of that. You see a permutation. So this is the first equality. The other one are generated in some sense by the first one. And this equality I mentioned. So the order in which the morphism appear in the right-hand side of the first equalities of the previous proposition. Equalities of proposition 5.5 and 5.6, exactly what I just shown, correspond to cyclic permutation, to the cyclic permutation so denoted like that, 2, 3, 4, and 3, 2, 1. So which mean you know that 2 maps to 3, 3 maps to 4, 4 maps to 2, 3 maps to 2, tac, tac, cyclic permutation. And these two cyclic permutations generate the alternative group A4, which generate the alternating group A4. So easy to check using. So you can check it by hand if you like, but you can also check it by gap with gap. So this group A4, which generate alternative group A4, the symmetry group of the regular tetrahedron. I mean orientation preserving. I guess I already mentioned that. So you keep up to considering this natural transformation. Up to this natural transformation, this monoidal tetrahedron has, for symmetry group, A4, exactly the symmetry group of the regular tetrahedron. And we will see later, more precisely, in what sense the the complicated shape of a monoidal tetrahedron can be replaced by a more symmetric shape. And in fact, you can also visualize it in 3 dimensions for the tetrahedron to be regular. Anyway, so now we will start the section containing the more complicated picture for me to draw, which is about the monoidal triangular prism and the proof of the triangular prism equation. In particular, one picture in this proof is very long to draw. So monoidal triangular prism and equation. Triangular prism equation. Okay, so exactly as for the previous section, we will first define the monoidal triangular prism. And so there are several ways to draw the triangular prism graph. So there is one we already mentioned before, but there are also equivalent graphs of a different shape. And to define the monoidal triangular prism, we will use another equivalent graph for the triangular prism. So for making the Dylan-Thurston picture in the introduction, it was more convenient to consider the usual graph drawing of a triangular prism. But for monoidal triangular prism, we will need another. So let me write that. Observe that the following 3-way observe the following. I don't need that. Following 3-way to represent the triangular prism graph. So the first one is the regular one, the one we already mentioned before. As I said, it is the one which is the most convenient to show the ID of the proof of the triangular prism equation using Dylan-Thurston picture. But the one we will use to modelize the monoidal triangular prism is this equivalent graph. So you have to convince yourself that these two graphs are equivalent. So there is a notion of isomorphism of graph. And so there is a bijection. I guess you can guess what is an isomorphism of graph. So it should be a bijection for the vertex. And then a bijection for the edge. So there is a way there is a very proper way to for the isomorphism of graph. So these two graphs, trust me, these two graphs are isomorphic. And so we will use this shape to modelize in the monoidal case. And there is another way which will be used later also, not in the monoidal case, but when we will consider more structure, like spherical fusion category, for example, it will be convenient to consider also this isomorphism, this graph, which is also isomorphic to a triangular prism graph. In fact, you can see the isomorphism between this one and this one because it's just as you visualize this one in 3 dimensions, and you look and you turn, you make a rotation in 3 dimensions of this one, and you get something like that, and you can yeah, you can see that. Otherwise, to see, so this one and this one, you can visualize it in 3 dimensions. Then it remains to consider this one and this one. This one and this one, just you just move this here, this here. So you get this, which is this is this is this, etc. And this is just this. So it's okay. So, okay. So let me do like that, which means we will consider this model here. So this section introduces the triangular prism in a monoidal category. Introduce the triangular prism in a monoidal category. So following the second representation of the triangular prism graph above. Following the second representation of the triangular prism above. As before, as for the tetrahedron, we all the morphism will be uniformly as like that. Okay. And then next, we will derive an equation from it, triangular prism equation for, so the equation will be only for the fusion case, for a fusion category. By evaluating it. So by evaluating the triangular prism, the monoidal triangular prism in with two way. Okay. Okay, so that I already mentioned in the introduction part. So now, concretely, what is this monoidal triangular prism? So we will need to introduce a list of notation for the morphism and for the object. They will have 9 objects, x1, x2 up to x9, and 6 morphism, alpha 1, alpha 2 up to alpha 6. And as I said, every morphism will be of this form. So there will be in the set of morphism between the unit object and a tensor product of 3 simple objects here. So definition. Monoidal triangular prism. Let's see the monoidal category. Category with left dual. Let x1 up to x9 be object. They don't need to be simple, in fact. Be object in C. Consider the following morphism. So we will need 6 morphisms. So let me check. I will. Sorry. So alpha 1 in set morphism between 1 and x4 tensor x1 star tensor x6 double star alpha 2 in this set x5 tensor x2 star tensor x4 star alpha 3. So there are 6. So x6 tensor x3 star tensor x5 star alpha 4 in C1 x9 tensor x1 tensor x7 star. So it remains alpha 5 alpha 6 C1 x7 tensor x2 tensor x8 star. Yeah. In fact, I realized that there is a shorter way to write this. I should just said alpha I is in the offset between morphism between the 1 and some yi with yi equal blah 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 blah. Y1 equal y1 equal that, y2 equal that. You don't need to write OMC, but anyway, it's done. So, okay. So you consider this 6 morphism. So something. Just 1 minute. C1. Okay. So let us. So we have the object, we have the morphism. Now we need to draw a picture. Let us define the labeled monoidal triangular prism as follows. Monoidal triangular prism as follows. Okay, so I will try to draw it quite nicely for the first time. And then I will need to draw it again or something similar. Maybe I will not, it will not be so clean because it will require too much time. But for this one, I will try to make it clean. So TP alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. Defined as follows. So the 6 morphism will be ordered as follows. So alpha 1 here, alpha 2, alpha 3, alpha 4, 5, alpha 6. Okay, so let me just try to make something clean. Okay, so maybe I need to be a little bit on the left. Okay, that should be okay. Okay. Now, the box. So as I said, I take my time to draw it for this first time, but then I will go quickly later. So later the picture will not be as beautiful as this one, but you can refer to this one to avoid any confusion. So, okay. Then you have the 3 objects. So x1 is here. So I will write the object later. Let me draw the string. So there is one evaluation map here, one evaluation map here, and here, here. Like that. Okay. Then, so we will connect all this. So this will be connected to the first here, here. So let me draw it cleanly. So co-evaluation map, evaluation map here. So it's not nice. Like that. I cannot do it. This is okay. And then okay. Well, just last time. Cannot draw it anyway. Like that. I should go quickly. It will be better if I do quickly. Like that. Okay. And this one. Okay. So don't worry. So this is here you have an evaluation map and a co-evaluation map and evaluation map. So it's really a zigzag relation. Okay, so I will do the same below. So like that. Okay. And here, like that. Here. So a co-evaluation map here. And evaluation map identity. Map identity. Of course, this one is bad. Okay. So I try my best to do something not so bad. So everything should be understood as evaluation or co-evaluation map or identity. So as before, I make this picture on LaTeX in the paper, so it will be much cleaner in the paper. So now, where are the objects? So X1 is here. So let me draw the object with this color. X1, X2, X3, X4 is here. X5, X6, X7 here, X8, X9. Okay, so you see, for example, alpha 1. So morphism between 1 and X4 tensor, X1 star tensor, X6 double star, which is okay. So you can check all the other, you get exactly what's expected. So that's okay. Okay, so this is the monoidal triangular prism, labeled by the morphism alpha 1, alpha 2 up to alpha 6. So as you can see, this is a number, or at least this is an element of and 1. So when 1 is a simple object which is not assumed, but when it is a simple object, then this is just a scalar. And when the field is algebraically closed. Yeah. So, okay. So as before, it is possible to prove some symmetries, but we will not do that here. Details, even in the paper, it's not done because we don't need this symmetry for this paper. But let me mention without proof. That you have a C6 symmetry. C6 the cyclic group of order 6. So without going into the details, we can, as before, into the details, which are useless here. In the spherical case, we can prove some equalities as in section 5 for the tetrahedron, monoidal tetrahedron, corresponding to the permutation 1, 2, 3, 4, 5, 6. So it's not a cyclic permutation, it's a product of two cyclic permutation. And the permutation 1, 4, 2, 5, 3, 6. Generating the orientation preserving symmetry group of the triangular prism. Generating the orientation preserving symmetry group C6, so cyclic group of order 6, of the triangular prism. That's possible to prove that, but we don't need here. Okay. Okay. So what time is it? Remain 10 minutes, 12 minutes before the pause. So let me check, let me state the most general version of the triangular prism equation. In fact, we will state several versions. Each version has more structure. And each more you have structure and more the version is symmetric. I don't know how to say. It's easy to easy to understand. I don't know how to say. So theorem. Triangular prism equation. So it is written for a pivotal fusion category, but with some extra work, maybe that can be stated for a general monoidal category. In fact, in some previous results, we had to assume fusion. I don't know for which symmetry we needed fusion. Yeah, for the tetrahedron. Anyway, here I wrote it for fusion, but I will not be surprised that that can be generalized for more than two monoidal with some extra weaker assumption than that fusion. So let C be a total fusion category. So this assumption could be made weaker with extra work. Maybe, but it's enough for this work, for this paper, for this course. So let A be the pivotal structure let alpha e equal 1 up to 9 and alpha e equal 1 up to 6 as before. So B object and morphism as before. In C as defined in the previous definition. Then so you will need to remember the natural isomorphism rho and alpha we defined before, because we will need. So the statement of the theorem will be without picture, but the proof will be with picture. Then, so this equation will involve some basis, B0, B1, B2, B3, and some set of objects, big O. So I will define this basis and set after I will write the equation first and define the notation after that. So sum beta 0 in B0 of T. So remember, T here is the notation for the tetrahedron. T of rho power minus 2 alpha 2 rho alpha 3 rho inverse alpha 1 beta 0. So this is the notation for the tetrahedron, monoidal tetrahedron we defined before. And so this is the four morphism you put. So this is the natural isomorphism rho we defined before. Okay. Times another monoidal tetrahedron. Alpha 5, beta 0 prime, rho of alpha 4, rho inverse alpha 6. So this is equal to the sum over simple object in the set big O we will define after, beta I in Bi, I equal 1, 2, 3. Dimension of X, T of another monoidal tetrahedron, rho inverse sigma beta 3 prime, rho alpha 3, rho square beta 1, rho inverse alpha 6 time. So we will have 3 monoidal tetrahedron, rho inverse alpha 4, alpha 1, beta 1 prime, beta 2 time, T, monoidal tetrahedron row inverse, alpha 5, alpha 2, beta prime, beta 2 prime, beta 3. Okay. So you have this general, the most possible general triangular prism equation in this class. Remember, it corresponds to what we draw as follow, equal to sum 1, 2, 3, and with something inside. This is what we show in the introduction part, and this is what we will get with extra assumption. So let me define the notation. So what about this B? So where BI and BI prime are basis, so I equals 0. I equals 0, 1, 2, 3 are basis of C1ZG. So I or G should be I or G. So I maybe. I will check that, and basis of that, and C1 star I. So this basis we already mentioned this basis in some previous lemma from lemma 3.2. And so the element here, you have beta 0, but sometimes you have beta 0, but beta 0 prime. Beta 0 prime means it is in B0 prime. So the map denotes the bijection from BI to BI prime. So remember, we have this. We define the basis for that and the basis for that, and we noted that, I don't remember, EI prime, and you have the usual bijection like that. Okay, then. So I will finish to write the notation, and we will make the pause after that. So maybe the pause will be shifted off by a few minutes. So, okay, with Z0. So we have to define all this Zi for I equal 0, 1, 2, 3. So Z0 is x1 tensor x2 tensor x3. And for I equal 1, 2, 3, Zi equal x tensor. So what is x? X, yeah. X is here. So X tensor yi where y1 equal x9 tensor x6 star, y2 equal x7 tensor the radial of x4, and y3 defined as x8 tensor the radial of x5. Okay. So this is how to define yi. So to get zi for I1, 2, 3, so we get that. So you see, this element are in the base, such a basis, defined like that. And finally, before we need to define big O, the last notation. And the big O here is the set of simple subobjects of both y1, 1y star, y2 star, y3 star, up to isomorphism. So the simple subobject of both y1 star, y2 star, and so both, I mean, not the union of all the subobjects, but it should be the set of simple objects, which is a subobject of that and that and that. There should be subobject for the three, up to isomorphism, of course. Up to isomorphism. And we are done with the notation. So this is, and of course, yes, rho here are the natural isomorphism as defined before, rho and sigma. Okay. So let me check where I so let me wait a minute. Yeah, and rho and sigma are the natural transformation from definition 5.1, if I'm not mistaken. Okay, so I have 3.2 check. Okay, so we will make the pause now. So pause. So you can stop. Okay, so now we will prove this equation. So the proof will be by picture and using some previous lemma. So I will try to make the proof as understandable as possible in a reasonable time. So the ID is to evaluate TP. So we will the monoidal triangular prism for the morphism alpha 1, alpha 2 up to alpha 6. So we will note it TP. So TP depends on alpha 1 up to alpha 6. But assume that alpha 1 up to alpha 6 are fixed, and just we'll use the notation TP to simplify. Anyway, with two different ways. Providing the left-hand side and right-hand side of above equation. Okay. So first, the left-hand side. So on one hand, observe that we can apply so lemma 3.2. So don't worry, I will explain what I mean by applying lemma 3.2. I will draw some preliminary picture, which gives the ID, and then the explicit picture. So with z equal z0 to TP. So we observe we can apply. So let me explain this lemma here. So TP here. So where is the TP? Here. You can consider two blocks, this block and this block. And these two blocks are related by three evaluation map. But if you make some tensor product, you can consider it as a big evaluation map for x1, tensor x2, tensor x3. So TP is equal to so you have the big block, the second big block, and the evaluation map Z, so equal Z0 equal. So let me draw it below. Equal x1 tensor x2 tensor x3. One tensor x2 tensor x3, which is equal to, by this lemma, sum of something like that. So you have that. You have a base sum over some basis ei prime, like that and like that. This is exactly what this lemma is saying. So you have something like that, and that can be written like that. So remember, we did that. Of course, the notation you use in the lemma are not the notation we'll use in this proof, but to get the idea, it is like that. Okay. So here. here. EI, I in I correspond to B0, to the basis B0. This is the notation for this statement, for the statement of this theorem. The notation of the basis is B0, but in the lemma, the basis was like that. And of course, you have B0 prime for that. Okay. Okay. So we can write. So we can apply this lemma with this big block. So let me recall again. The block. This is one block. This is the other block. And this is the evaluation map of x1 tensor x2 tensor x3. So you just need to, in some sense, you just need to copy and paste this big block here and here, and replace alpha I by beta 0, alpha I prime by beta 0 prime, etc. So you get the following. So picture TP equal okay. So you have alpha 1, alpha 2, alpha 3, okay, beta 0, beta 0 prime. So I will need to shift a bit on the left. Okay. Alpha 4, alpha 5, alpha 6. So what I need a bit more. Yeah, I can shift more. Okay. Okay, that should be okay. Okay. So now the boxes. Boxes. Okay. The object. So this was a choice to uniform the shape of the morphism, all of this form. You can maybe you can also write some alternating way by allowing something like that or something like that. But I'm not sure. It may simplify something, but make something else more complicated. So I choose to uniform everything. Okay, so you see, this is this corresponds to that, this corresponds to that, and this corresponds to something we will draw here. Okay, so that like that. So then it's quite similar as before. Maybe I should draw it in single time, like that, here. Okay. Here. Okay. Here. So this one will be like that. Okay. Here. And finally, the third. Okay, so yeah, that should be straight. Otherwise, it makes no sense. Okay. Anyway. Okay, so identity, evaluation map. Identity, co-evaluation map, evaluation map, identity, evaluation map, etc., etc. So you have zigzag everywhere. These zigzags are required to make the picture. But some zigzag here will not be required if you write this algebraically. But of course, when you make a picture, this makes everything much more clear. I try, in fact, to, as an exercise at home, I try to make the formula, algebraic formula for even for the tetrahedron. It's really a mess, and you cannot understand properly what this means if you just do it by algebraic formula. So here the picture are really, really relevant. Okay, so we made this. So I forgot the sum because there is a sum, and I forgot to write the sum. So I can move this a little bit on the right. The problem is that I don't have enough. I hope it will take everything. Yes. Okay. So I forgot to write the sum. Sum for beta 0 in the basis B0. And so you have beta 0 prime, which is the prime is, as I said, the bijection between the basis B0 and B0 prime. So even if I write only the sum over B0 and not B0 prime, in fact, the notation prime is well defined. It is explained here. The prime is a bijection. Okay. Okay. And so as you see, we almost have the left-hand side. We just need to move a little bit. We need to move that here and to move that here. Then we will get the usual form for monoidal tetrahedron. And we can move this using, this move can be realized using some zigzag relation. So, okay. So I will apply zigzag relation to realize this move and this move. Okay. So by some zigzag relation, we realize the move so x3 x alpha 3 alpha 6 right. Which mean then TP equals sum for beta 0 in the basis. So we move. So you can look what should happen if you make such a move. So we move that here. So you will see, you will get alpha 3, but this will be here. So you get something like that. So you have two monoidal tetrahedron, this one and this one. So I will draw it one up and one bottom. So the first alpha 3, alpha 1, beta 0. Okay. Alpha 2. Okay. So the box. C object. So this one is not okay. Okay. So you, as I said, you have this. So this is here. So you have to convince yourself that this is exactly what we get by some zigzag relation. You can get that. This one should go there. This one is there. This one here. Okay. So okay. So you look at that. You focus on that, and you visualize this move, and what you get is that up to zigzag relation. And the second one, so in fact I have some extra space. So the second one below, so beta 0 prime, alpha 4, alpha 6, alpha 5, the box, the object, tac. So similarly, we move alpha 6 here, and you visualize. In fact, it is symmetric. So this is the mirror symmetry, not mirror symmetry, but this is some symmetry of the other one in some sense. So you get something like that. Here. So this one, where? So let me draw this one. Okay. This one. This one. And finally. Okay. So again, you have to convince yourself that this move up to zigzag relation provide this monoidal. It's not yet the shape of a monoidal tetrahedron. We have to apply now some natural isomorphism, rho or sigma, because here you see it is not exactly what we want. We want something straight here. So we have to apply some move. In fact, we will consider this move and like that, which would be usual. So we will have to consider rho of alpha 4, rho inverse of alpha 6, etc. Idem for here. So again, by some zigzag relation. So this move, so this is equal to like that, like that, like that, like that. So this is rho of alpha 4. And then you have that. And then you have rho inverse of alpha 6. So this is realized by a zigzag relation. And then you just have to replace alpha 4 by rho of alpha 4. And then you will get exactly the expected shape for a monoidal tetrahedron. So by some zigzag relation, we get that Tp equal sum for beta 0 in B0 T of rho. So alpha 2 we need also to do the same for here. So here alpha 2 we need to apply, we need to consider rho inverse 2 times. So surely something because in the usual shape the first string should go here, but here the first go here, this one go here. So if you apply this one and this one, then the first, so this one, then the first go here, which is what we want. So you make something and something, etc. by zigzag relation, and so you can replace by rho inverse rho power minus 2 of alpha 2 to get the exact shape of the monoidal tetrahedron, etc. The same idea, rho of alpha 3, rho inverse of alpha 1, beta 0 times T of rho inverse of alpha 5, beta 0 prime, rho of alpha 4, rho inverse of alpha 6, which is the left-hand side of the equation we want to prove. So the first step is done. Now the right-hand side, which is the more complicated to draw, in fact. The idea is, in fact, for the right-hand side, we will need to apply the lemma we call resolution of identity. So the right-hand side is really more complicated. So on the other hand, and we can apply proposition 3.8. So what we called the resolution of identity. Resolution of identity on TP of alpha 1, alpha 2 up to 6. 3 times with T equal Tj equal alpha j star. J equal 1, 2, 3. So in the proposition 3.8, the notation was T. Here we consider that, but to do not use a star, we just write Tj. Okay, and big O of Tj, the set of simple subobject of Tj. The set of simple subobject of Tj up to isomorphism. And the basis from the previous lemma, 3.6, always the same. So this lemma where we prove the existence of a basis, we use this specific basis. So now we can apply the resolution of identity. So let me first come back to the monoidal triangular prism, which is here. So we will apply the resolution of identity here one time, here one time, and here one time. No, I'm wrong. Sorry, we apply the resolution of this identity. So this is an identity, and this identity, and this identity. So 3 times. So here, so we will replace this identity by a sum of something involving the basis. So yeah, here 3 times, here. Okay. So TP. So let me try the picture globally before writing it in details. And you have something here. So we don't draw here, we just draw here, here. This one, and then we don't draw the rest. So we apply the resolution of identity here. 1 time here, 1 time here, 1 time here. Here is T1, T2, T3. So by T1, T2, T3, I mean the identity of T1, the identity of T2, the identity of T3. So we apply the resolution of identity. We apply 3 times the resolution of identity on identity of Ti. I equal 1, 2, 3. So we apply the relation of identity on identity of Ti for I equal 1, 2, 3. Okay. So now here will be the big picture, the biggest picture of the course. So this is equal to proposition 3, 8. And so as I said before, to the sum for Si in big O of Ti, I equal 1, 2, 3, sum beta I in Bi, so this basis, I equal 1, 2, 3, and I need more space here. Product. So okay, move that bit. So I can move everything. Okay. Okay. Product for I equal 1, 2, 3, dimension of Si time something. And the something will be the big picture. And I'm afraid I have no enough space here to draw it. So, or maybe I can draw it quickly, because I have only 7 minutes to draw it. And I guess if I take my time, I will have no time in 7 minutes. Okay. So time, I will try. So beta 0, beta 1, beta 1 prime, alpha 4, alpha 1, beta 2, beta 2 prime, beta 3. Yeah. Okay. Remove that. Beta 3 prime. Okay, alpha 2, alpha 5, alpha 3, alpha 6. Okay, and I need also some pivotal structure. AS1 inverse, AS2 inverse, AS3 inverse. Okay, the box. So I will need some more space here. Okay, then this box, wow, I really have no enough space here. This box, this box, this box. Okay, so I need a bit more space here. Beta 1 prime. Okay. Okay. So this go like that. This go like that. That's okay. Yeah. Yeah. And here. Now this is easy. Easy this one. This one. Okay, similarly. This one here. This one here. Here, like that. Like that. Now the more complicated part. Okay, so at least one I can do here. Okay. 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 Now this one. Oh wow. So now it will be hard. So this will go here. So, okay. And almost done. Almost done. This will go here. And this one will be connected to, so yeah. And this one, finally, here. And this one here. Okay. So as you can see, I strongly recommend you to go to the paper because it's really hard to draw it. Let me just, I will just write the object and we will stop after that. X2, S2, S3, X5 here, X6, X4. Okay. So, yeah, this is the better I can do in 5 minutes, but you should understand everything in terms of evaluation and co-evaluation map. There is no crossing, there is no crossing, nothing touch, there is no touching here, no crossing. This is just evaluation, co-evaluation map, zigzag relation. And this is just the application of this. The resolution of identity here. So this is replaced by this thing. And here it's replaced by this thing. Here it's replaced by this thing with some sum. So this is the base, the basis we considered before. So we have to look at proposition 3.8 and lemma 3.6 where we define the basis. And this is exactly what we get. So this is just the application of the resolution of identity 3 times. and we get this shape. So tomorrow, we will see that this shape is in fact something very simple. You can see it S1, S2, S3, and then some trace. And so that can be highly simplified. Then we will be able to decompose that into 3 parts. And similarly, this part with some zigzag relation and row and will be exactly will be the shape of a monoidal tetrahedron. And so we will get the right-hand side. Okay, so we will stop here. Tu peux arrêter.